Okay, so the emphasis for today is more on um, ways that a contributor can get involved with the library, whereas yesterday it was more on how an analyst would use the library and some of the theory behind it. Um, so today's going to be a lot more involved with the code. And to spare you the details of the Rust, I've prepared a bunch of examples that can be done from Python, starting from, well, over the last year or so, we've put a lot of work into making it so that you can extend the library from Python, and it makes it a lot easier to do prototyping and kind of demo um, how you would add new transformations and measurements to the library and combinators. So I'll basically start with some implementations of really basic transformations and measurements, kind of a recap of yesterday, but we're actually doing it ourselves. These are things that are already in the library, but seeing how they work is um, potentially very helpful. And then we'll do an example of building a combinator that does chaining to piece together transformations or measurements. Um, we'll do more discussion on composition, um, creating your own transformations that use custom domains, and we'll just see how far we get. There's quite a bit in here, but that's the plan for today. Um, and at any point in time, if people have questions, of course, as always, please speak up. So remembering yesterday, we had a transformation for clamping data. How might this look in the actual implementation? Remembering before we had to put together 6 different pieces. Make user transformation. So those pieces were an input domain, a metric, output domain, output metric, a function, and a map. So as I'm writing examples today, I'm going to choose simpler versions of these constructors that aren't quite as generic. So in this case, we'll just do a clamp on vectors of integers instead of the more general case in the library where it's vectors of anything, so long as it's numeric. So there's a module in the library for there's a module in the library for the various kinds of domains that you can build. Um, for this clamp, we'll want to use an atom domain, which is describing the space of all um, atomic types of a certain type, atomic values of a certain type, with some potential extra descriptors, like if it can have nullable values or if bounds are set on the values. We'll also use vector domain down here. So it takes as an argument an atom domain. So you can kind of build up more complicated domains out of smaller domains. Domain type is int. So this guy is the space of all integers. This is the space of all vectors and integers. And then we'll say the input metric is symmetric distance. Insert delete distance is a variation of the metric that is sensitive to the ordering of the data. Can be important if you're trying to account for details of finite data types, whether things can overflow or not. But I'll keep things simple for now. We'll say symmetric distance here. The output domain is going to be the same thing as the input domain, except now we have another domain descriptor that limits the set of values. So bounds is a tuple of int and int. Now this is the set of all vectors of integers that are bounded, and symmetric distance. It doesn't change the metric, so pass that in as the output metric as well. And then the function, we'll just use NumPy. Flip x between the bounds. Now, you'd expect that if any one record changes between neighboring databases, then after clipping, you'll still have the same property, only at most one record will change. Or more generally, if you know at most dn records can change, then the resulting data sets after clamping will differ by at most dn records. So this is essentially re-implementing one of the constructors in the library, but as I mentioned, a little bit less generic. And if we look for clamp, oops. This is the corresponding Rust code. It's a little bit more generic in that you can pass in the input domain and input metric, and these can vary based on the data type or chosen metric. There's an extra assertion here that data that's passed in is not null. So if we're in the situation where we're clamping and values in the input domain can have nulls, then this will fail at construction time, not at runtime when you're actually dealing with the data. It does a little bit of work to build the output domain, and then it calls another lower level constructor with these pieces. Does this all make sense when it comes to the just building a really simple transformation from Python? All right, good to hear. Similar thing for making a sum.
So can you actually run that example?
Oh yeah.
Do you just try that?
Yeah, that's a good idea. So let's say we'll clamp between 0 and 1. And clamp. We pass some data in, let's say -1, 0, 1, 2. Then clamps as expected. And if we want to run the stability map, then this should be the identity function.
The stability map is like taking the value of the input metric to an output metric, right? Like that's the translation.
So we're saying if input data sets can differ by at most 2 with respect to the input metric, then after applying this function, the corresponding output data sets can differ by at most 2 given the symmetric distance. Thanks for the question.
Do you have an example when it won't be the identity?
So yes. Here's an example, a resize transformation. and make it a bit bigger. So in this case, you build a transformation. The input domain is a vector domain, and the output domain is a vector domain, but it has a known size. And the function that we're using in this transformation will, if there's too many records in the data, then it'll sample down. If there's too few, then it'll add some extra imputed values by constant. So in this case, like you might consider the case where you have two neighboring data sets and one is equal to the target size and one is one less. Then if we were to impute one record up on X versus on X prime, you would do nothing to it. Then the difference between those two data sets is now an addition and a removal, because it's unlikely that the constant will be the same.
Yeah. But you're using symmetric distance instead of add one. Or...
Yeah, so
I mean, maybe it's too much like load, yeah.
Yeah, so here it's you can always use the symmetric distance instead of change one.
Okay.
Like symmetric distance is the more general metric in all cases. But so the way you can represent bounded DP is you have a metric that does unbounded DP, but then you also have a restriction on the domain that the size is known. And then really the key differential between bounded DP and unbounded DP is just the existence of a dataset descriptor, a domain descriptor about the size. Yeah. So yeah, there's a little case where it's too stable. And there's also other cases where this distance type is not just one number, it's a triple of three numbers. When you're doing grouping, for example. And that can be more finicky.
Yeah.
Oh, and also, I don't know if you've heard of like Thielsen regression. That's another case where it could be case stable, depending on how many pairs you make. But a lot of them are the identity function. When you have the same metric in the input and output. Okay. Everyone's cool with that?
Maybe just a quick question.
Yeah.
Would you have like remove one neighboring relationship in this case for this reshape?
For this, what was the last one you said? What was the last word you said? I missed it.
So could you have the remove one neighboring relationship for this reshape function?
Yeah. So for resize, if I again, the output metric here is still like add or remove, essentially. Symmetric distance is counting additions and removals. And the reason, like you would typically expect this to be, this is a conversion from unbounded TB to bounded DP. So you might think, oh, the metric is going to be change one instead of symmetric distance. But it.
And if you, let's say, if you do this resize, and then you do a mean on some axis, won't this padding essentially bias the output? Or
yeah, it could potentially bias the output. Well, like there's many branching paths you can take. You could say maybe you estimate the dataset size beforehand, and then you bias that down a little bit with post-processing, and then use that as your target size to make it very unlikely that you'll introduce bias. But the trade-off there is that you'll add a little bit of variance. So
can an adversary exploit essentially this to leak more? Because essentially, I imagine you pad with zeros or something like that, right? If the adversary sees something that's biased towards zero.
Well, the math all works out, fortunately. So if you consider two neighboring data sets, then both of the neighboring data sets would have to gain a lot of zeros because they'll be close to each other. So it'll tell you that there you may have potentially had to impute a lot of values, but the difference between those two neighboring data sets is very small because for both data sets, you've had to impute a lot of data and introduce a lot of bias.
But this needs to hold even if it's like only one element, right? Let's say you have like only one.
Mhm.
And you remove it in this remove neighboring relationship, and then you add it with zeros.
Mhm.
Then if the adversary sees that it's something biased towards zero, it's kind of obvious which
Mhm.
you know?
Well, I guess the next thing you would do after this is clamp. And then let's say you were to do a sum, then the sensitivity ends up being, as you would expect, the difference in the bounds. So it would be a case where the privacy loss random variable is maximized, but it still doesn't exceed the upper bound. Great questions. All right, so okay. I thought I lost a cell somewhere, but I'm good. So mixed sum has a similar structure. The output domain is going to be just the single scalar, no bounds. Int. We're going to expect that the input domain has bounded data. And then the output metric is absolute distance. Okay. All right, so to recap, we have we're going to make a transformation here where the input domain consists of bounded data, vectors of bounded data that can differ by additions and removals. And it's going to emit a data set that's a scalar. It's in this new scalar domain where the difference between adjacent data sets in this new domain is measured in terms of the absolute distance. And then in order to compute this, really all we need is just the sum primitive directly. And then the stability map is going to be, well, however many records we can change. Let me unpack. One cell, and then this will be dn divided by 2. So it's divided by 2 there because no, I have the wrong one. I was thinking about resize, so I used the wrong stuff. X is the value of the lower bound. There we go. In the worst case, we can make a difference of dn times whichever is bigger, absolute value of the lower or upper bound.
Isn't it also absolute value of the upper bound?
This doesn't make it wrong, but it's not necessary. If U is negative, then L is always smaller than it. So it'll always be a bigger value.
Okay, yeah.
Yeah.
Yeah, makes sense.
Sure. Okay, so then it's a very similar, yet again, structure for measurements. In this case, Laplace mechanism will take a scale parameter. We'll do a simple version where it's just taking in a float, or taking in an integer and outputting an integer. Integer doesn't have to have bounds. Digits differ in terms of the absolute distance. For measurements, you don't need to specify an output domain. The output measure, the name changes there, because we're measuring a different kind of thing. Instead of data sets, we're measuring distributions, distances between distributions. We'll call this mixed divergence. So we want to upper bound the divergence between resulting distributions. And then keep in mind that all these mock implementations are not accounting for issues like mentioned in Ilya Miranov's on sensitivity, or on the on sampling of floating point numbers paper, and other complications that have to do with implementing things on finite data types. So as I use this, recognize that it's not good practice. So then location, it's distribution centered at X with a scale as set in the constructor from up here. Now in this case, dn is essentially the sensitivity in terms of the absolute distance. So you might be familiar with that big triangle delta divided by scale gives you epsilon. That's what we do here. So if I were to call this with a scale of, let's say 1, what is integer? We have error. Oh, right. I should have renamed this to privacy. They have different semantics. So notice in this case, I'm adding continuous Laplacian noise to an integer input. I don't want to go through the bother of building a discrete Laplace sampler and using that. So we'll again keep things simple. So in this case, this is just looking at the Laplace mechanism. What does the map do? It translates a sensitivity into an epsilon. And the input should be an integer. So this gives you an epsilon value. Think of the output is
Or the earlier, the input has to be because
because up here. Because the metric is measuring distances. in terms of an integer data type.
And then on the previous, like on make sum. Should we, on the input domain there, do we need to specify that it's int or?
Oh, you could if you want to. In this case, it looks at the type of the bound to determine what it should be. Okay, so we now have, let me pull this out.
I have a question.
Yeah.
Is it really, it's not epsilon, should be e to the power of epsilon, right? Because you specify the distance in terms of, or it's just a like,
So the max divergence does directly correspond to epsilon.
Okay.
Like epsilon is, you can think of it as an upper bound on.
oh, it's already with the log. So that's
yeah,
why,
yeah.
okay, it's a log, right? Like, okay.
Yeah. Uh, Yeah, so like epsilon is an upper bound on maximum divergences.
Mhm.
And the log is kind of already there.
So if you will, for example, use some other metric, you might return a tuple, like to get epsilon delta or like.
Right, so you might say fixed smooth max divergence. It's a very long name, and I've been thinking about changing it for a long time.
Okay.
Then the output here would need to be a tuple. First value is epsilon, and the second is delta. And this should also work. Yeah. Or you could do smooth max divergence and output. I don't know if you can nest lambdas like this, but make a curve inside for. All right, so I'll back these out. And there's also ways that you can define your own measures from Python. So I might get to that later, or I might not. So now we have, well, we have two. Let's say the bounds are the same as up here. Okay, now we have three. Now we have two transformations and one measurement. How do we get them all to glue together? So we have another constructor. It takes in F2 and F1. Transformation. All right, so the input domain. The input domain would be the input domain from the first transformation. So F1 dot domain. The input metric is F1 dot input metric. The output domain is F2 dot output domain. And the output metric is pulled off of F2. Function is going to be a composition of both. So we'll do F1 X and then pass that into F2. And the map is F1 is pretty simple, but this is actually not quite right yet. You also need to check to see that the output metric of the first transformation matches the input metric of the second, and so on, for domains. And I've kind of written that out here. So this piece here is here. I'll get rid of this. We can just skip forward. Checks that both of the functions you pass in are transformations, and checks that that they conform. Similar idea for chaining a measurement with the transformation. Actually, let's call this first. Make chain TT. Take in T sum and T clamp. And this should give us sum. And then this is a measurement for BP sum. Make chain a measurement with a transformation. We'll take the Laplace measurement, and the transformation for the clamp sum from here. And everything stitches together. And if we were to call it, then obviously you get a DP release from one, that stitches everything together. And of course, every time I call it, then it uses different samples from the distribution. Is this making sense so far? Yeah.
It's more just like a question, like on the type checks up above, presumably. Could have as long as it has the right attributes, it'd be okay. Like, I guess it's sort of like, are we actually requiring that it's actually an instance of measurement? Or as long as it had.
I think there's some inherent special meaning to calling it a transformation or calling it a measurement. It's saying that the behavior of the function is governed by the stability map or the privacy map, with regards to the various supporting elements.
Okay.
So if it isn't a measurement, then like if the thing you pass in isn't a transformation or a measurement, then I would say that if you were to stitch things together anyways, it then wouldn't necessarily be a transformation or measurement.
Okay.
Okay, so this is all well and good. We've built a bunch of simple transformations measurements. We've built our first example of combinators that take other transformations and measurements and build new ones. How would you do, for example, composition? So we have many flavors of composition out there. I'll start with just non-interactive composition. I built this little helper function that checks to make sure that the input domain and input metric and output measure for a whole set of measurements is the same. If they're different, then this would try to impact multiple values and fail. So just a quick shorthand to keep everything simple and short. This mechanisms variable is going to be a list of measurements. And what we want to output is a new measurement. The idea is if you call that measurement, then it should call all the constituent measurements inside of it. So make user measurement. the input domain will, let me do like this. Yep,
It would be like without topic on that. Because we have the measurements already, right?
It's-
so
it's going to build a new measurement that calls all the other measurements. And the map on it will be the composition of all the D outs from all the measurements.
So all of them are going to get the same input.
Right, yeah, they all have the same input domain. And you might have, remember that measurements don't have output domains, so they could all have different output.
Yeah.
Data types. Domain, input, metric. The function is lambda, it takes a little list comprehension here. It'll just iterate through all the mechanisms and run them, return it in a list. And the stability map is, or the privacy map on this is going to be the composition. So en notice that the output measure is generic. We don't necessarily know that we can just add them up. You could say maybe the output measure has a way to compose. Given dn and let me pull this out to a function because it's a little heavier than expected. That takes in a dn. Call each mechanism, the map on each mechanism, and now you have a bunch of privacy losses, one for each mechanism. Then you could say compose given a dn and all your d outs. Does this make sense? It would definitely be the case where you can't just add things up if, say, each of the d outs is a curve. Then it's a lot more complicated to figure out how to build a new curve. Or if it's an RDP curve, then it's a lot simpler, but it still wouldn't just be additive unless you define how to add those curves together. For convenience in this presentation, I'm just going to go and simplify this. And we'll assume that the output measure is either max divergence or fixed smooth max divergence. So then it'd be basic composition. You got a bunch of DMs. All right, so let's use it. We do have a measurement from before, MDP sum. I'll just make a couple of them. And it's going to make a new measurement that calls it twice. Delete it as that and pop that in there. So now we get multiple releases. If we were to call the map, then we should get twice the privacy loss. Yeah, 2.0. Any questions on this? I feel like I'm moving quickly when I'm typing, but moving very slowly in concepts. Um, advanced composition, I'm not gonna go and implement this one, but, advanced or strong composition. But the ideas are similar. So in this case, we'll say, the privacy measure has to be approx DP, where all the parameters are fixed. There's no curves involved. We use the same helper function to pull out input domain, input metric, input measure, and the privacy map gets a little more complicated. You got to lift the formula out of the paper and implement it. The function doesn't change; it just calls all the mechanisms, but the privacy map is now you substitute in the formula from the paper. Does that make sense? Great. Interactive composition. So interactivity is going to bring in variables. We still have the same general idea in that we're collecting 5 pieces and putting them together. This time, though, the function, when you call it, returns something that is like a state machine. It's a queryable, and you can interact with it. So in this case, you have to specify your distances up front, unfortunately, in order to correctly implement the function, which is a shame, but I haven't seen a way around it at this point. So the way this works is we have a function that takes in the data, and the response from this function is going to be a queryable. And the queryable is essentially just a function that can mutate some state. And the state is listed out here on this line. The state is going to be your data, your input data set distance, some the static output privacy loss parameters, and the supporting elements. The only thing that will change in this function as you the only thing that will change in this queryable as you interact with it will be the output dataset distances. We'll pop one off each time a query comes in. So let's say a query comes in. The query should be a measurement. The query should match the supporting elements on the query that's coming in should match those of the compositor. If this all passes, then we can pop one of the privacy losses off of the state and check to see if it satisfies that level of privacy. So all of this is checking to make sure that the query that the user is asking is it is a measurement, it is DP, and it has the same input metric, domain, privacy measure as the compositor that it's interacting with, and that the amount of privacy it advertises, it will consume when you run it, is less than the amount that the compositor is configured to accept.
I have a question. So what we're saying here, basically, it's interactive in the sense that we don't know which queries are going to be executed.
Right.
But the budget for each query in its sequential order is already set from the beginning. Like I'm committing, I'm going to do 1 epsilon, 2 epsilon, 1 epsilon, 3 epsilon. But only after I've seen the first result, I can choose.
You can choose which
query to do. But I've committed already to the amount of.
Right.
Yeah, this is the D meets.
Yes, yes. Yeah, so there's lots of directions you can go with compositors. This lets the queries be dynamic, but the distances be static. And you get theoretically, generally speaking, tighter composition this way. But you might not want to have that. You might want to have privacy losses that change for like, okay, so I've seen some output, some DP output. Now I want to choose the next query, and it has a dynamically chosen new privacy loss. This wouldn't support it, but in that case, you would use an odometer or a filter.
Like, have you seen? Oh, for example, MWEM would work something like that.
Yeah, you
Yeah,
could
okay,
you could do MWEM with this.
yeah.
You could do DPSGD with this, assuming you're not dynamically changing noise parameters as you're training. And so you can build a lot of things out of this. And I'd say if you can build it out of static distances, then you should, because you're going to get better bounds depending on which measure you're using. But you notice that this, while it gives you interactivity, it's a little bit more work up front. You have to specify the supporting elements. You have to specify the distances, whereas up here it was not necessary. And up here. This is still doing static distances. It's just that there's kind of a different argument in why you can still use composition based on static distances for these non-interactive compositors. So I don't have an example where you implement composition for an odometer or a filter, but the general idea there being you don't make a measurement, you make an odometer. And you don't have a privacy map. And the thing that you return, the queryable, has a way that you can pull and ask it, what would my privacy loss be if DN is this? And then a filter is a combinator. It's a combinator that takes in an odometer, and it takes in an upper bound on the privacy loss, and it outputs a measurement. And so that resulting measurement, you can spawn a queryable from it, and you can dynamically choose privacy losses and queries as you go. And at some point, it will refuse to answer queries because you've consumed your budget. And in that case, you can make it a measurement because you know ahead of time that the privacy loss is bounded. So you can make a map. Yeah. All right, so here's an example of making a vector valued sum. Initially, in order to build a DP sum measurement, you want to have a way of clamping the norm. So there's a function that clamps the norm. It might do some shifting around the origin. The main thing I wanted to point out in this example is you can make your own domains from Python. So previously I was using dp.vector domain. dp.nparray2 domain is calling, oh, this is a long function, a lot of checks to do. It's calling user domain, and in order to build your own domains from Python, you create kind of a string descriptor of what the domain is representing. You make a function that can check if a value is a member of the domain. And you might want to carry around extra domain descriptors that you can access later. So for the clamp transformation, it's getting in a two-dimensional array. And all we know about the two-dimensional array is that it has float data. And then it's going to emit a two-dimensional, the domain of two-dimensional arrays with a bounded norm in each row. This is also one stable, just as the clamp was. But the main thing we're gaining from here is additional descriptors, domain descriptors that can be used by future transformations, like a sum transformation. So in this case, the stability constant is based on the p norm of the origin plus the norm. The output metric is, well, it's either L1 distance if P is 1, or L2 distance if P is 2. So you can say that resulting data set of, it's going to be one vector and change by at most Bn times a constant when the input changes by Bn records. I might be going too fast. I see a lot of confused faces.
I don't think it's about this thing, but just flagging for a little bit now. So,
So this is a sum of a vector under a specific norm. That's
Yeah.
the idea.
Yeah. So the input is a data set that's a two-dimensional array.
Mhm.
And you know that each row in that array has bounded norm.
Mhm.
So it can change by at most norm in terms
So
of
norm is
L1
the
or L2
bound
distance
of
from the origin. Yeah.
Okay.
And so if you just assume origin is 0.
Yeah.
Then you can say that if you were to take the p norm of each row, it'll be at most this variable norm.
And this, okay, and the transformation is just to get sum each row separately. Get,
Yeah, so it sums each column.
oh,
So if you know each row has bounded norm,
yeah.
and you sum along the columns, it clocks it down into one vector, d-dimensional vector, then you know that the sensitivity of this vector is bounded. It's finite.
Yeah, okay.
So this is kind of what you would expect to see in DPML. It's a little bit more handwritten than you would see there, of course, because a lot of these computations would be done in PyTorch or TensorFlow, but the concept is the same. Like if you use an Opacus, then when you make a DP gradient, you can think of it as a, it's going to be a probably more than a two-dimensional array, but you can think of it as a two-dimensional array if you flatten it. And then sum up the stimuli axis, observation axis. So a lot of the constructors in the library are written in terms of lower level constructors. So we could build another measurement that takes the clamp from above, this one here, and then takes the sum from here. And then it uses vector valued loss measurement. I'm just pulling that directly from the library instead of implementing it myself. Things kind of can be used interchangeably. This right shift operator is calling make chain TT or make chain MT. And so the privacy properties of this should follow from the privacy properties of each transformation and the combinator that chains.
So if you were, for example, putting on that Gaussian mechanism,
Mhm.
is it going to scream on you or?
Yeah, if you were to use Gaussian here, let's just try it, then Gaussian. If I run that, yeah, it screams. Oh, I didn't run this of. It should fail here. One of my handwritten, this guy here requires floating point because it's not accounting for some of the details you'd expect. Okay. Yeah, expected data of type L2 distance got L1 distance. It's not happy. It's getting a metric that's L1 instead of L2. If I bring this to 2, then it should fall through. Yeah.
So like Gaussian, for example, expect either L2, it's expecting either absolute value difference, like there is a, okay.
Yeah, so if it's a vector valued noise mechanism, then it wants some LP
Okay, yeah.
distance. And if it's scalar, then it's absolute. And it's really picky. You could say that it's okay to pass an L1 distance into the Gaussian mechanism because L1 is always smaller than L2. I think I got that right. Orders might be backwards, but instead of making the Gaussian mechanism more general to take any LP norm less than 2, you could instead make a transformation that has an identity function as the function, and the stability map on that is also the identity function, but the output metric is L2 distance. And then to prove it, you'd say that there's monotonicity of norms. Yeah. So we're trying to keep things small and self-contained and simple. So great. This is and if I run this, I get nice random data. It's a vector. The whole thing should satisfy 0.5 rows of CTP. All right, I have like 25 minutes left. Any other questions before I dive into the next example? Is this making sense? Okay.
It's pretty deep, pretty fast if you're not that experienced with DPOs. Or any requests them to make something they're interested in or help how you go about it for plugging.
All right, I'll just keep on trucking then. I hope this is interesting to people and learning a lot. Okay. So yeah, you can do a lot with Python nowadays.
That's new. It wasn't there 1 year and
Yeah.
it's like,
So
yeah, that's my last point.
yeah, a lot of the stuff is new. A lot of the things like making queryables from Python, making custom domains, metrics, and measures from Python were added in Q1 this year. Main thing is I want people to be able to just implement things and add things to the library without needing to run Rust, because it seems to be a pretty big stumbling block.
And is there a way when you write in Python to make it secure in terms of floating point and run like in an easy way, or it's just like
there's a lot more utilities available from Rust, because we had to build them up from scratch.
Yeah.
I'd like to make more of those internals available to Python so that you can do those, but haven't gotten to it at this point. You definitely can do things on your own. There's a Python package that allows you to do controlled random floating point arithmetic.
So
Controlled random.
infinite,
Uh, and you can also just implement all the formulas yourself to account for those kinds of things. It's a lot of work. But yeah, it's no reason why you can't do it. Given the time, I think I'll just show the implementation. So if you want to implement, say, a randomized response, specifically in the case where the input data is just a single Boolean, we're not going to consider multi-category randomized response. You can say the input domain is the space of all bools, so it's a pretty simple set, true and false. The input metric is the discrete distance, so the distance is considered to be 0 if x and x prime are equal to each other, and 1 if they're not equal to each other. And then the output measure for randomized response is just going to be max divergence for period EP. In this implementation, I'm going to limit the probability to be somewhere between 0.5 and 1. The probability is, the interpretation is that it's the probability that you return the true input. It's the probability that you don't change anything. You just pass it through. And if you were to work out the proof involved with this, then the privacy loss would be probability divided by 1 minus the probability. So here in our privacy map, if we know that datasets differ by distance 0, then we'd have 0 privacy loss. It's kind of a weird edge case, you could say. Whereas if they can be different, then your privacy loss will be this quantity. And the function involved takes a sample from takes a random Boolean with probability of true being prob, and it uses an XOR to potentially flip the input. And think minimize. So this is the same. This is the same as an implemented Rust. Rust is a little more picky about this math. But if I say prob is equal to 0.75, we're more likely to keep the input. Then in randomized response, it's there. If I were to call it with a small data set of true, then has a 75% chance of returning true. It will return false sometime. What doing wrong? It loves that true. I got one false in there. There it is. There's a false.
Okay.
So that was unlikely, but I guess that's the penalty of working with randomized algorithms. All right, so I think you guys get the map, so we'll move forward. Any questions on how this works? Notice that this is a local DP algorithm. Just like with central DP, which all the examples we're in so far, you can do chaining for local DP things. So there's some work going on right now to add rapport to the library, which you can think of as like a Bloom filter transformation, chained with a more general version of randomized response for the measurement. And then you would imagine that all of the you would use it locally and aggregate those on a server somewhere and use some post-processing to convert those into your probabilities.
Just dumb math question on this one, is it that we'd expect like 1 out of 8 to be false because we
Mm.
expect 1 out of every 4 to be random?
So this is the probability that you don't mess with the input. So it would be 1 out of 4 probability that you return false. Let's see. I'll run it some more, see if we get more. Is it false?
This,
Maybe 0.5, then. Let's run it a bunch of times. I'll have to mess with it more. I think we have some distributional checks in there somewhere, but or I've done some distributional checks in the past, but
Okay.
I'll check to make sure. All right, so 15 minutes and I wasn't expecting to get through everything, but I just didn't want to run out of stuff. Yeah.
Which is maybe unrelated to this, but it's related to how randomness is generated.
Mhm.
Usually, when you use DPML libraries, one of the biggest pains is that you want to have some sort of reproducible way of running an experiment. Can you do that with OpenDP?
Can you wouldn't-
like a starting seed, and then every time you get the same.
Yeah, so it's not supported right now. We're doing all our sampling from OpenSSL. But I want to change that. So I think I'd like to talk with you a bit more
Yeah.
about how we're doing random sampling. I have a PR open that changes the sampler. And from there it would be easy to add a way to set a seed. It's not so easy to set a seed in OpenSSL, so that hasn't really been an option.
I think all libraries out there anyway. So one use case that's extremely annoying is that, for example, if you're subsampling something,
Mhm.
you might want to fix the seed of that. You might want to see the same batches.
Yeah.
For example, but you would want fresh noise, so it's you might not want to fix the seed for everything.
Got it.
It's always very annoying. And you usually do X go around that.
Yeah, so you might want to have a way to pass the CSPNG into
Yeah,
mechanisms, which brings its own complications. Like you don't want to have you don't want to make it too easy for people to break things. So it's a little bit of a touchy topic. And so finding the right happy medium is something we'll have to explore. Yeah. Okay, so there's so the exponential mechanism, I think of it from an implementation perspective is not a mechanism, but as a very broad family of mechanisms. Like you're not going to go out and just implement it. You're going to implement some kind of flavor of it that works for a specific set of candidates. One set of candidate that is pretty easy to grapple with is when your set is finite. say you have a problem where you want to select privately from maybe 10 different candidates. And it's more likely to choose, based on the data, candidate number 7. This is the kind of mechanism, this is a flavor of the exponential mechanism that lets you do that. Typically, when I read about the exponential mechanism, I see it in terms of exponentiating a score for each candidate, and then sampling a uniform 0, 1 random variable, and finding the first candidate whose cumulative probability is above that uniform sample. In the library, I ended up not doing it this way because it's very difficult to give good provable guarantees and when you're dealing with floating point numbers. So another equivalent way of doing it is report noisy max with Gumbel noise. And in that case, it's equivalent, instead of doing all this work and building a vector of likelihoods and normalizing them into a vector that adds up to 1 and doing all that jazz, you instead add a sample from a Gumbel distribution to each score. Say like higher scores means it's more likely you pick it, and then only returning the index of the highest score. So if you were to try to use this in the OpenDP library, you would see, let's say, make report noisy max, Gumbel, and it has the same API as this, but again, a little bit more general. We can put domain scale. Notice that for this case, the way that we measure distances between data sets is with L infinity distance. So what you get is a vector of scores in, and what you're saying is that each score can change by at most the L infinity distance, the bound on the distance. So you might say on an adjacent data set, all the scores can change, but each score can change by only so much. And the fact that the amount that the scores can change is limited is what makes it possible to give privacy guarantees.
So it is expected from the user to write the score function with the transformation. OpenDP, and then you get all the goodies.
So given that things are implemented in little pieces, if you have a score function, you can write it in Python and chain it with this report noisy max Gumbel.
But then can you track about all the float?
If you can what?
Track on all the float point issues if that's.
So the piece you implement in Python, it's up to you to implement the floating point finite data types correctly. But the piece that's implemented in Rust, the report noisy max Gumbel, is floating point safe. I'm able to sample Gumbel random variates to arbitrary precision.
Yeah.
So that one's fine.
I mean, yeah, but I'm mostly worried, about this stuff about the sensitivity work, right? Like,
right.
Like
so,
if I do some sum in, yeah.
Exactly, yeah. If you go and implement the scoring function yourself in Python, then it's very likely that it's vulnerable to the same kind of things that was mentioned in the paper. Yeah. And it's kind of it's definitely a downside. Like we could make it so that no one can use library APIs to do their own things. And then it would be super secure because it would only be our things.
Yeah.
But then it would not be as flexible.
But you can just do, like, if you can express in transformation the right ways to do it.
So we do have a score transformation for quantiles, for example. I think there's a blog post with another example of building a transformation from Python that I think happens to be immune from these kind of things. But yeah, it's up to you in the end.
Yeah.
If you want to roll your own. And maybe in the future we can get better about providing utilities that make it easier to do that. But one step at a time. Yeah, so I was going to mention this quantile. Lots of math here. But this is a score function written as a transformation that here's the body of the scoring function. It's ripped right out of Adam Smith's paper with some minor adjustments. And then the output metric is the infinity distance. This is going to return a vector of scores, one score for each potential quantile that we're trying to choose from. And the sensitivity is dependent on the quantile, depending on the alpha parameter for the quantile. And then you can roll it up into a higher level measurement that does everything for you. It's a little bit easier to work with. You have a score transformation, you chain it with a mechanism. I guess in this case, it doesn't matter which one you pick. Port noisy max gumball. And then there's another function that's applied afterwards as post-processing that but this guy only selected the index of the best candidate. Now we go back to the candidates and index into those. So this kind of a neat thing to keep in mind is if you have post-processors, you can just chain them on after as normal Python functions. I'm basically out of time, but you can implement lots of things with this. Here's an example where I've got a domain defined in Python that's used to implement an above threshold mechanism. I wanted to mention this because I know you'd be around. This is based on some talks I had with Shlomi, I guess last fall. So this is not the private selection from private candidates mechanism directly. It's from Thomas Steinke's paper, and it does it for OpenDP.
So this is already in Rust, or this is?
This one's not in Rust, and I want to add it to Rust, and I was going to have, depending on how far you get in your summer project, to help implement samplers for this. And yeah, the streams are also not in Rust, but this is how I want to implement them in Rust.
It's a cool, like you have the way to express it, prototype in Python, and then
Mhm.
yeah, it's cool.
I have a lot of stuff prototyped in
Yeah.
Python, and I just want to add it. But I'm also trying to implement polars, so. Yep. So I hope that the OpenDP programming framework is a bit more understandable now that you've seen some examples. You can express a lot of things in it. And it's pretty fun to take concepts from the literature and just apply them in this framework.
Thanks, all, Mike.
That's what I have to say.
Yeah.
Thank you. Yes.